Hello world, it's Craig. I have had a number of requests to formalize and share my PROM to serial port adapter doodads. They've shown up in a few videos, and next to my logic analyzer and soldering iron, these are probably some of my most used tools on my bench, maybe even more than my logic probe, because even after I get a system up and running, if it doesn't have a native serial port, then I still have one of these things hanging on it just so I can communicate with it. So I have two versions of these. This one is for 1702s and 1702As, and this version is for all the other PROMs. This one has a few more features, and if there's interest in these little tools, then maybe I'll have a separate video for this one. But this first video is just going to be about the version for the 1702. So the purpose of this little tool is to add a bidirectional serial port to any system that has a functional PROM socket. So if you have a board that you don't know anything about, the board is broken, you don't know where any of the ports are, or any of the UARTs or anything, all you need is for the board to be able to pull its address, or to start pulling instructions from the PROM socket. And as soon as it can pull instructions from the PROM socket, then you can put this little board in and immediately have a serial port so that you can communicate with that board and start running software on it. So even if I'm running old hardware that does have a serial port, sometimes there's hardware issues with the board, sometimes I don't know the address of the UART, or it's a UART I'm not familiar with, I don't have code with, I haven't actually tested that UART, I don't know how the port was created. Sometimes I have no documentation for the board whatsoever, so I have no idea how that serial port is implemented. But on nearly every system, there's going to be a PROM socket, and getting the processor to fetch that instruction from the PROM socket is usually, fairly straightforward. And as soon as that system is operating to the point where the CPU can fetch instructions, pop in this PROM adapter doodad and begin communicating with the board. So at the end of this ribbon cable is a DIP termination plug. So that goes into whatever PROM socket that you have on the board. That brings the signals over to this adapter, and that moves the PROM over to this ZIF socket. So whatever PROM you have in that board, you can move over to this ZIF socket. And this board has a RS-232 serial port, or if you prefer, it can just use a TTL level signal if you want to use a USB to serial adapter, but TTL. And there's a jumper here to select which you're using. Put the jumper on the left for the serial port, put the jumper on the right for the TTL adapter. So now once communication is established, then I can begin writing and using software tools, and that makes diagnostics of a piece of hardware so much simpler once you can communicate with that, and you can start fishing around in the software for various ports and things. So that makes reverse engineering, debugging, documenting, and everything else just so much more efficient once you are communicating with that board. I keep a set of little PROMs that have code in them that help me for that. For example, this little guy right here, this is the first one that I'll use. If I can get it out. Okay, this is 1702 serial bit delay value detect. So it uses what I call the brute force method. It is a serial adapter at 00FE00FF. So that's the address of this adapter. So you do have to know what the address is of whatever PROM you have this thing plugged into. It's RAM-less, so that this code doesn't require any RAM at all. It says reset and enter a U character until the baud rate bit delay value is returned on the terminal. So this basically tells me I can use whatever baud rate my terminal is, and it doesn't matter what speed the processor is. This will tell me what bit delay value I need to use, because I'm bit banging this serial port, what bit delay value I need to use. Okay, so then I have a second little PROM that I'll put in, and this guy is a PROM search. So it's at the same address, it's RAM-less still. It says install a duplicate PROM in the target sockets and reset, and this will then display on the terminal the address of whatever sockets you're looking for. So this is the PROM search. Once you've got the PROMs, and the next thing we want to know is where's the RAM. So this third little guy I pop in, and it is a RAM map. You pop this guy in, and he will display on the terminal all of the RAM that it's found. So once you have the serial port value, you know where the PROMs are, you know where the RAM are, then there's a set here, and this is kind of a complete set of probe software. This says a 1702 probe 1 of 5, Autobod. This one is for address 0. It's ramless still. Reset and then enter a space character to get the menu. The menu includes map RAM, map the ROM, fill the RAM, dump, and then download Intel hex files. So really, once you can do all of those things, you pretty much have command of the situation. You really have the upper hand in the diagnostic battle. So after utilizing all this ramless code, then I move over to more specialized code that uses the RAM and creates a stack, and then progress becomes much quicker when you can do simple things like calls and returns. What I have in this board right now, for example, this is just a bootloader. So I have, this one takes 2. I have one of them at the 0 socket, and then one up here at the last socket F. And this is just a bootloader. It allows me to download Intel hex files into RAM, and that's pretty much all that this one does. This, by the way, this is a from Intel Intellect 8 or 80, and this is my reproduction version of that. If you're interested in that project, you can build these. You can build an Intellect 80 or 8 with my reproduction boards, but this is one of the original Intel ones. Okay, so again, using all of these, it doesn't depend anything on the system. It doesn't matter about the clock. It doesn't matter where the RAM is. It doesn't matter where the ports are, and so forth. The only thing you need is the first ROM where the processor fetches instructions, and then after that, you're good to go. So of course, when we talk about this little adapter, the fundamental problem is to add the serial port is that by definition, a PROM socket is read-only memory. And the system hardware has no mechanism for writing out to a PROM socket. So on this board or any of my other boards, when it comes out to a PROM socket, there's no write strobe. There's no way of writing to a PROM socket so that you can send any data out. This is only reading. And so what this board does is it gives you a bidirectional serial port only by reading from the memory. And the way it works is it hijacks 2 addresses from the PROM for use by the serial port. So all the other PROM addresses are just passed through. It takes 2 of them that it's hijacks, and those 2 addresses then are stopped. They're redirected onto the board rather than coming over to this little ZIF socket. So except for those 2 addresses, the rest of the PROM memory is just accessed normally. On this version of the board, the 2 addresses shanghaied are the 2 highest or the most significant addresses of the PROM. And those are just the 2 addresses specific to this specific socket, not the whole board, because we're still relying on the rest of the system to decode the memory address and select one PROM socket. Then within that PROM socket, the PROM usually decodes the rest of the addresses. So this is 1702, so there's going to be 8 addresses coming over to here. We're only utilizing the top 2 of those 256 bytes in this EPROM. So now one of those 2 addresses is used to set the transmit bus status, meaning it puts it into the asserted state, and the other address is used to clear the transmit bit status or put it back into the idle state. So for simplicity, the least significant address bit is used as the transmit data bit. So if we read from one of the 2 hijacked addresses of the PROM, and that address ends in a 0, then the output latch on this board will be reset. And if that address ends in a 1, then the output bit will be set in that latch. And the serial line will be in the idle state. Because keep in mind, the RS-232 transceivers like the 1488, 1489, the MAX 232, and so forth, they all invert the signal. So to get a minus 12 volt idle on the serial line, or the equivalent on the 5 volt TTL line, then we need to output a logic 1 to the MAX 232. So we would write basically to an odd address so that we would get a 1 in the least significant bit. Now if you watched a previous video where I put a serial port on the solid state music cards, that's pretty much exactly the same concept. That design that I put into this board was just based off of what I had been using on these little adapters. And the thing is, on this solid state music board, the RS latch was set or reset by reading from a nicely decoded input port. But when working on some older hardware, things are not as clean, and there's a couple of issues that need to be addressed. And that's kind of why this looks a bit more complicated than you would think it is. And the first is that the 1702 is a MOS device that is referenced down from VCC, not up from ground. It has a number of plus 5 volts and minus 5 volt inputs, but it does not have a ground input on the 1702. Since we're limited to the signals that are coming off of the board to this, we don't have a ground pin. And so there obviously isn't going to be a ground for this. This isn't referenced to ground unless we ran another line, from this over to the board. And because I wanted to use standard TTL devices on this, this board needs to create its own 0 volt reference. If we look at the schematic, here is the ground reference portion of the schematic. The board doesn't actually need a ground. It's more or less floating after all, somewhere between -9 and +5 volts. It just needs something that is 5 volts less than the 5 volt rail. And we're going to call that 0 volts. To make that, there's this 7905, which is a fixed negative 5 volt 3-terminal regulator. The current sink is the -9 volt rail, meaning that's where the regulator is going to dump the current in order to pull this 0 volt reference down away from the 5 volt rail towards 0 volts. The reference voltage input pin is called ground on the device because they don't know any better how we're using it. It's connected to the 5 volt rail, and the output is now the reference voltage minus 5 volts, meaning the 5 volts below the 5 volt rail are pretty near 0 volts. The current through the 7905 is just the current from the onboard logic devices, and I've used all LS in this family, so it's a very modest current draw. There's not a lot going through this 7905 here. But there is one little thing, and that is that in case there's another source of 0 voltage reference other than the one we just created, say there's a true common line, somewhere else, there's a bit of protection built in by this little germanium or a Schottky diode that holds the 0 volts that this board creates just a little bit above a hard 0 voltage reference. So that means that this board's 0 volts that it's created is going to run 200 to 300 millivolts above a true 0 voltage reference. And without that little offset, if you were to connect a true ground that is different than what this created as a 0 volt, then that regulator will try to bring the rest of the world down to what it's defined as 0 volts, and it can start to dissipate a lot of power in that regulator, and that becomes a real finger burner. So there's a very important jumper on this board, and that's a jumper that enables or disables the onboard 0 voltage reference. So that jumper should be removed whenever the board is getting the ground from somewhere else. So you shouldn't rely on that diode for protection. And while that diode does give a little bit of wiggle room, it's best to check everything else to see what connection is providing a 0 voltage reference. If it isn't being provided somewhere else, then put that jumper in, or the board won't work reliably. Now, since we're connecting to a terminal, the most logical source of a 0 voltage reference is the terminal, like the shell or the ground pin on this. And some of my terminals, most of my terminals actually, but they will hold the ground on their serial shell and the ground pin near 0 volts. And when using those terminals, then I don't need to generate this on voltage 0 volts, and so I take that jumper off. But other serial cards, internal cards, and some of my USB to serial adapters, they are completely floating with respect to ground. So you can have a serial adapter on this, and this board is floating with respect to ground, and what will happen is you'll find that the ground on this will float up to about 3 volts. So none of these TTL devices have enough voltage to operate because this whole board is just floated up, or the ground on this board is floated up to about 3 volts. And in that case, this 5 volt light won't turn on, the LED won't turn on, so you put the jumper in and it creates the 0 volt. There's also a little barrel connector on this, and chances are that whatever you're using for the power supply, if you're using a little wall wart or a desktop supply, that's going to be completely floating. So all this barrel connector does is to provide more 5 volts if the host can't support that little extra load on the 5-volt rail. So all total, there's 3 sources for 5 volts, and they're all connected together. There's the host. You can get the 5 volts off the host. You can get the 5 volts off the barrel, or you can get the 5 volts off of your little USB to TTL adapter. But those are all just tied together, and it's not usually a problem. Single quadrant power supplies connected together, they tend to get along fairly well. I'm far more worried about the grounds playing well together than I am the 5-volt power supplies. Now, there is a jumper here. Those sources can be isolated by cutting traces and then using this jumper, but if it's misconfigured, bad things can happen. So it's better to just leave those jumpers shorted together and forget about it. The final warning is that when you're first configuring this board, check that this regulator, first set everything up, take the jumper off, try to run it without the 0 volts. If it isn't running, you can check everything to see that there is no 0 volts being provided, and if that's the case, then put the jumper on to get your 0 volts, and then check that regulator to make sure that regulator isn't getting too hot. Normally this TO220 package can dissipate just fine. It'll barely be warm to the touch, if at all. All right, so the 0 volt is the first thing that's funky about this 1702 PROM adapter doodad. The second issue that will come up is the 1702 was so forgiving. It was such a slow device that it really allowed some sloppy address decoding and chip select designs to be implemented in hardware. Data outputs were just being wired together. Devices were slow. Just insert wait states and everybody still went home happy. But remember, we only have the data that's available to the PROM socket. So we're not privy to any actual read strobes or data valid strobes. And so this board cannot fall prey to glitches in addressing in address decoding or the chip selects. And many of these older 1702 systems, they would set up the PROM address, assert the chip select, and then just insert wait states or 2, and then they would come back and read the data. And even without inserting wait states, they can be careless with their logic, and frequently there's timing mismatches that create glitches in the address decoding and the chip select, and that was just because the 1702 really didn't care. So rather than taking the chip select at face value, like we would in a newer system, as soon as we see the read strobe goes low, we would say, okay, everything else must be stable. You can't do that on these 1702 systems because they just weren't that concerned about it. We have to de-glitch that chip select, or we risk passing any glitch that we see in that address and chip select onto the transmit data bit, and we would then be making false start bits. And the terminal would think that we were actually sending a character out when it was just glitches that were coming on. What we have to do on this device is we only are hijacking the top 2 addresses. If we ignore A0, we take the other 7 addresses along with the chip select into this 8-input NAND. At that time, the socket is fully addressed and selected, and if it's any address other than the top 2, then the regular active low chip select is passed through to the ZIF socket, and the PROM in the ZIF socket experiences a normal read cycle and puts its data onto the bus. So when we're at address FE or FF, and this device is in the socket that's being selected, the chip select will go low, but we're inverting it down here. So all the inputs of this NAND are going high. The address is in one of the top 2, and this socket is being selected. So there may be many glitches there as the system narrows down an address and the address decoder, and then it selects the socket, and the 1702 is so slow it doesn't even see most of them. Worst case, it puts data out that has to be updated as those addresses settle down, but the system probably isn't going to care. Just like the processor waits until everything is stabilized, we have to wait on this after we see the address be selected and this board be selected before we make any decision about updating the transmit bit. And that's the purpose of this first monostable in the circuit. As soon as the top 2 signal is asserted, indicating that the data is for the serial port and not for the ZIF socket, this one shot creates a hold-off period. And that's long enough to guarantee that everything is stable. So we don't do anything during that one-shot period until that ends. And when that one-shot period ends, then the trailing edge latches the state of the top two status signal into this D flip-flop, and that creates this strobe signal. So if at the end of the one-shot period the top two signal was not asserted, meaning the monostable was triggered by a glitch that's since settled out while we were waiting for this monostable to go back high, then the input of this top two latch is false, its Q output will remain false, and the next flip-flop, which is the transmit bit latch, is left unchanged. So if it was a valid output to the port, then at the end of that monostable period, the top two signal at the D input will still be asserted. That will get latched in, and the output of this first latch, which is the strobe signal, will go high. That low to high transition will then clock in the data input to the second latch, which is the least significant bit of the address. If that least significant bit of the address is a 1, then the transmit data goes high, and if it was a 0, then the transmit data goes low. So software-wise, this is just like bit banging out any other serial port. Normally we would rotate the output bit into the same position or some position into the accumulator, send it out the SOD line if it's 8085, or out to some memory address or output port if it's something else. And then we would rotate to the next bit of the character and repeat until it's done. But with this adapter, we look at the output bit, and if it's a 0, we do a memory read from a memory address ending in FE, and if the output bit is 1, we do a memory read from the address ending in FF. As I mentioned earlier, this whole board is running on the top two addresses of this specific PROM socket. So we're still relying on the rest of the system to decode the upper part of the address to assert this socket. And that means that the full address of the serial port depends on which socket is used. The base socket is convenient because there's a good chance that this one starts at 0. So on this board for the Intellect 8, if we have it plugged into this first socket, the address of this serial adapter board would be the address of that socket, high byte 00, giving an address of 00FE or 00FF. If we plug it into the next one, it's going to be serial port would be the address 01FE and 1FF and so forth. And here in the last socket where it's plugged into now, its address is 0FFE to clear the transmit and 0FFF to set the transmit bit. So as for the receive data bit, so that's all we need to do for the transmit bit. For the receive data bit, anytime we do a read of either of the top two, the data that we get back is the receive value from the serial port. And that comes in as the most significant bit in that data byte. So we just do a memory read and look at the most significant bit, and that's going to be the received value of our serial port. So when you're expecting a character from the terminal, you just continuously read from an odd address until the start bit is detected like a normal bit bang job. Since the odd address is being read, the transmit will remain in the idle state. Now in this, the receive bit comes in as the most significant bit, and actually in this one it comes in as both the most significant and the least significant bit. The reason I have it come in on the most significant bit, or on this board actually in both, is that occasionally it can save you a few bytes of code. If you get one of these and you're trying to fit as much as you can into a 256 byte 1702, you'll appreciate saving that 1 or 2 bytes wherever you can, and the flexibility of having the bit on each end. Once you have these on your bench, you'll come up with all sorts of handy software tools, like some of the ones that I showed you that I keep in this little case. I generally use 2400 baud. 2400 baud is 416 microseconds per bit, and the values for the one shot that I have on this board give me about a 2 microsecond hold off for the glitch filter, and most of the time that's long enough to skip over the glitching and still leave enough time to get the receive bit back to the processor without having to add additional wait states. Now occasionally I've come across systems where I need to use different baud rates, or sometimes the glitches continue a really long time. So on my most recent version of this, I have put in this little potentiometer because I need to be able to stretch out that glitch hold off period, to the hairy edge of that 2400 baud, and I can use that trim pot to stretch that out. There's also an upper and a lower resistor here so that you narrow the window that trim pot is available for. But you know, truth be told, 99% of the time I can get by without that trim pot, and you know, that's caught me before where I had that trim pot misadjusted, and I thought I had a problem when I really didn't. So actually in this most recent version of the board, I have a jumper here. You can put that jumper in and it bypasses that trim pot and takes you down. This is a 5K in this resistor, so this 5K and that 1000 puff capacitor give us that couple of microsecond delay time. So I put the jumper in so I don't have to fiddle with that pot, because 99% of the time, like I said, that works. And you know, I might even suggest that you don't bother putting in that trim pot until you come across a situation where it's needed. You know, just put in that jumper because it's much simpler and it's not going to catch you by surprise sometime. If you want to use other baud rates other than 2400 baud, then you just get the appropriate RC values off of the 74123 data sheet. Or you know, I have one of these made up where I just have the trim pot. I don't have any of the little resistors here that define or narrow the window of that trim pot. I just have a trim pot in there. That lets me put in, you know, I can run it all the way down to 0 when I need to. I can run it all the way up. But I only use that board when I have it on a logic analyzer, so I can actually see the bits come in and I can adjust that trim pot to wait until all the glitches are over, but not so long that the read cycle is almost over and the processor doesn't get the data that I'm looking for. So if you have the trim pot, be forewarned that if you extend the glitch filter too far, the whole read cycle will be over before the glitch monostable relaxes and updates the latch. So that glitch filter needs to be just long enough to skip over the glitches, but still leave enough time for the output bit to get latched, or for the input bit to get stable on the system bus and latched into the processor. I'll put some in the user's manual. I'll put some logic traces so you can actually see what's going on. I'll show you the the Goldilocks. I'll show you some that are too short, just right, and too long, a glitch hold off period. Okay, that is enough information to get going with this adapter doodad. It's a pretty easy build. There's no exotic parts, and writing software tools for it is straightforward. Now, as usual, I have a few extras of this board because this is I tried a couple of versions since the older my original one that I've been using. So I have a few extras of these boards, and as usual, I'll give these away with the typical provisos. And first is that there is a little mistake on this board that needs to be patched. The second, that I would hope you would want this enough that you're willing to pay for the shipping. And the third is that you will build it and give me any feedback that you have on this. So as for the mistake, there's actually two, and they're both related to this JP1 jumper. When I grabbed the footprint, I forgot to use my shorting version. So this is the jumper that is the 3 power supplies. So there's a jumper there, and I meant for those to be shorted together, and I didn't grab the shorting jumper, or I didn't grab the shorting footprint. So when you build these boards, you need to just put a short across those 3 little pads. The second is that I mislabeled the silkscreen on that, but if you're just going to short those together, then the 5-volt source silkscreen doesn't matter because you're not going to be using that jumper. So as long as you short those together, that mistake on the silkscreen is immaterial. So if you want one of these boards, you work with 1702s, leave a comment below as usual to set your place in the queue, and then email me so we can arrange the shipping. The link to my contact page is in the description, as well as links to the board build files and the documentation project page. So I know the 1702 isn't everybody's cup of tea. If there's interest, I can polish up the design and release the version for the other EPROMs because it is a handy tool. And this one has some other nice features on it. Okay, well that's it for this video. I will talk with you later. Thanks for watching. Bye-bye.